If we depict 3D objects, often we use wiring models, but these models in some cases can be ambiguous. Therefore, algorithms of visibility are used. The Z-buffer algorithm essentially keeps track of the smallest Z-coordinate, also called the depth value, of those points which are seen from pixel. These Z-values are stored in what is called the Z-buffer. This algorithm can process points in either order. It displays also dynamic scenes. It has the application in other algorithms. At first we explain the algorithm and the calculation of Z-coordinate. The first step is initializing of two two-dimensional arrays. The array zbuff, which represents Z-buffer, is initialized at the maximum of Z-coordinate, on the value Zmax. The array mbit, which represents frame buffer, is initialized at the background. As a second step, we move along each polygon P. We do projection of a given polygon, then make its rasterization. Next, for every point x, y of polygon P, we calculate its Z-coordinate as follows. If we have polygon P expressed by his analytical explanation by next formula, and if C is not equal to 0, then Z-coordinate we can express by following fraction. If we use line coherence and x1, y1, z1 are coordinates of the first pixel, then Z-coordinate we can calculate as follows. If delta x is equal to 1, then value of Z-coordinate is Next, in algorithm, we compare Z-coordinate of the point xy with value in Z-buffer on position xy. If the Z value of the point xy is less than value in the Z-buffer, it means that this point is nearer to the viewer than so far tested points. Then this point is assigned to Z-buffer and the point is depicted on the screen. Now we illustrate this algorithm in action on a single example, the cube. The screen is divided to 4 parts. In the upper left part is a pseudocode. value is a two-dimensional array, which is representing Z buffer, where we will store the Z coordinates. In the bottom right part is a frame buffer, and in the upper right part of the window there is depicted one surface of the cube in raster, which is processed. The pseudocode is stepped by single lines, and in other parts you can follow the current process. In the algorithm we initialize Z buffer at the maximum value of Z coordinate 250 and frame buffer at the background color black. As a second step, we move along every polygon P, which will be depicted. The first polygon, which we are going to process, is painted green. We do projection and then rasterization of this polygon. Raster of depicted surface is represented by a grid. Next, for every point, we calculate Z coordinate. For this pixel, the value of Z coordinate is 30, and its color is the same like the color of the polygon, green. Now we compare the calculated value with the value at the corresponding position in Z buffer. If the calculated value is less than that stored in Z buffer, we assign this new value to Z buffer, and its color is stored to frame buffer. In our case, the calculated value is less than the stored one. Therefore, we assign this value to Z buffer and the pixel display on screen. In this way, we go through each pixel on this polygon. Furthermore, we depict the back surface of the cube. This surface is purple color. Like in the previous case, we do its projection, rasterization, and for every pixel, we calculate its Z coordinate. The value of this pixel is 50. We compare it with the stored value in Z buffer. You can see that our calculated value is larger than the stored one. Therefore, we will not replace it. We also will not change the color of the screen and on the frame buffer. The operating point you can see in a frame buffer in a box. The next 2 points will also not be stored like the previous one. The value of the following point is less than the stored one at the corresponding position. Therefore, this value will be stored in Z buffer and its color in frame buffer. On the screen you can see the depicted point. go through every pixel of this polygon. If we display other surfaces, we would go through the same process. This algorithm is suitable for displaying scenes with many surfaces, but when it operates on raster level, we cannot create a smooth display image. And we cannot create a transparent object. If we have two faces with different sizes and identical z coordinates, the result of displaying is ambiguous. The second animation presents algorithm of rendering mathematical surfaces by means of a floating horizon. If we render the graph of two variables given by a formula z equals fxy, we approximate the sought area by polylines. We expect that the sections are parallel with x-axis and that they are drawn from the front to the back. Drawing the first two sections of the graph, we have the cover of the graph given. If we draw the third section, we display only the parts which are over the upper horizon or under the bottom horizon. Now we explain this algorithm. In the beginning, we initialize the upper horizon at the minimum and the bottom horizon at the maximum. Then we draw the first section, which is visible, and we change the horizons. For each next section, we take the point of polyline, which approximates the graph section, and we compare it with values in horizons. If the value of z coordinate is bigger than the value at the upper horizon, we display this point as follows. The display point will link with the previous point of this section and with the same point of the previous section. If these points are also visible, we link it, and if they are not, we use linear interpolate for calculating the intersection of this link with the horizon. If we have the point drawn, we change the cover. If the point is less than the bottom horizon, we draw it by the same method, and the value is assigned to array DH, which represents the bottom horizon. We present this algorithm on the two-dimensional mathematical function. On the screen you can see the pseudocode. Under it, there are arrays UH and VH representing the horizons. On the right side of the screen, there are two windows. In the upper part is the given graph depicted step by step like the algorithm is progressing. Here we can follow the z-value of the operated point. Under this, there is the cover of the graph. At first we initialize the horizons. Then we draw the first section of the graph and change the cover by the horizons. In the window with the cover, we can see that the horizons are identical. When we draw the second section, the horizons and the cover are changed. When we draw the third section, on the screen we can see it in the green color. We must respect the visibility. The operated point is depicted on the graph and on the cover by red color. For each point of this polyline, we compare the z-value of the point with the corresponding value in horizons. If the value is bigger than the value in the UH array, we draw the point. If the value is less than in VH array, we also draw it. For the next displayed point, we proceed by the same method. We compare the value of the point with the value in the horizon, and according to the result, we draw the point or not. The calculation of the visibility test will be easier if we operate in a raster. It is not a good way to display quickly growing graphs. In such a graph, there appear disconnected parts. Appel's algorithm operates in object space and assumes that one edge is a conjunction of two surfaces. The first step is determining normal vectors of the surfaces. Then the surfaces divide to visible and invisible after the scalar product of a normal vector and a direction of projection. If it is negative, vectors create an obtuse angle. The surface is visible. If it is positive, the angle is acute. The surface is invisible. Now, we create the set V of potentially visible edges and the set C of contour edges. The edge is potentially visible if it is a conjunction of two visible surfaces. The edge is invisible if it is a conjunction of two invisible surfaces. It is contour if it is a conjunction of one visible and one invisible surface. The contour edges belong also to potentially visible sets. If we have a non-convex object, we need to detect if any potentially visible edge is not covered by other surface. The point where the visibility is changed is in a projection plane given by an intersection with some contour edge. Now, for each potentially visible edge, we determine its intersection with contour edges as follows. If P is a view direction, EI is a potentially visible edge, and CJ is a contour edge, then the function intersection returns in NJ plus 1 or minus 1 after visibility change in a given point. If the result of this formula is negative, then Pj equals plus 1, and if the result is positive, then Pj equals minus 1. Then we sort out these segments. We calculate the cover for one outer point and go through the segment of edge. If it is visible, it means n equals 0, then we display it. In the end of the segment, we change the covering after nj plus 1. We do the same for each potentially visible edge. Now, we illustrate this algorithm on a single non-convex object. On the screen you can see a pseudocode of the algorithm. Under it there is a window where the n value is displayed, and on the right side there is the given object. The first step is initializing. Then we determine normal vectors of surfaces and divide the surfaces to visible, its normal vectors are green, and invisible, its normal vectors are gray. edge set C, it is turquoise. A potentially visible edge set V, it is red. Other edges are invisible, they are gray. Now, for every edge from V, we determine its intersection with contour edges. For our given edge, we have one point of intersection. We determine covering for one outer point. In our case, it is n equals 0. From it follows that the first segment will be displayed, and then we will change the covering. Now n equals 1. It means that the other segment will not be displayed. You can see it in gray color. The other edge has not the intersection with the contour edges, and the covering of the outer point is n equals 1. Thus this edge we will not display. We continue through each edge from V. As this algorithm assumes that every edge is a conjunction of two surfaces, we cannot use it for displaying objects where several surfaces have one common edge. Such an object can be seen on display.